A star is a large mass of gas with a core temperature that is high enough to initiate nuclear fusion reactions, resulting in the radiation of energy. Stars are classified based on their surface temperature and luminosity. The luminosity of a star is the rate at which it radiates energy. This is also a measure of the total power emitted by a star. However, while the power of a light globe might be in the order of 100 watts, the Sun's power output is approximately 3.83 times 10 to the power of 26 watts, which is referred to as 1 solar luminosity. This value is often used to express the luminosity of other stars. For example, the luminosity of the star Achernar is about 3,150 solar luminosities. That is, Achernar is 3,150 times more luminous than the Sun. Luminosity depends on the radius and temperature of a star. Large and hot stars are more luminous than small and cool stars. In contrast to Achernar, the small nearby star Epsilon Indi outputs only 0.22 solar luminosities. The brightness of a star is a measure of the intensity of light seen some distance away from it. It is the energy received per square metre per second. Brightness depends on both the luminosity of the star and the distance of the observer from the star. To understand this relationship, visualise a star surrounded by an imaginary sphere. The star gives off energy uniformly in all directions, which penetrates the whole surface of the sphere. So the brightness can be expressed as luminosity divided by the surface area of the sphere. Since the surface area of a sphere is 4 pi r squared, brightness equals luminosity divided by 4 pi r squared. So this relationship describes how the brightness of a star at distance r from an observer depends on both the luminosity and distance of the star. Note that brightness is inversely proportional to the square of the distance, which corresponds to the inverse square law. Let's apply these relationships to some examples. Fomalhaut is 25.0 light-years from Earth and outputs 16.6 solar luminosities. Pollux is 33.9 light-years from Earth and outputs 43.0 solar luminosities. This information can be used to prove that both stars have approximately the same brightness as seen in our night sky. For Fomalhaut, brightness equals 16.6 divided by 4 pi times 25.0 squared. The calculation results in an answer of 2.11 times 10 to the power of minus 3 watts per square light-year. For Pollux, brightness equals 43.0 solar luminosities divided by 4 pi times 33.9 squared. This gives 2.98 times 10 to the power of minus 3 watts per square light-year. Therefore, both stars have similar brightness when viewed from Earth. Epsilon Indi has a brightness of X at distance 11.8 light-years. At what distance will Epsilon Indi have a brightness of 4x? We're going to look at the steps involved in answering this question. From the inverse square law, we can deduce that the ratio of brightness 1 to brightness 2 is equal to the ratio of distance 2 squared to distance 1 squared. So x over 4x equals r2 squared over 11.8 squared. Therefore, r2 equals 5.9 light-years, meaning that if Epsilon Indi was half the distance to the Sun that it is now, its brightness would quadruple. Another notable feature of a star is its colour. The energy radiated by a star is determined by its surface temperature. At different surface temperatures, the suite of wavelengths emitted changes. In order to understand why this is the case, we need to briefly look at blackbody radiation. A blackbody is a theoretical construct that absorbs all radiation that falls upon it. When it becomes hotter than its surroundings, it begins to radiate electromagnetic energy of its own, which is known as blackbody radiation. The radiation is distributed continuously but not evenly across the wavelengths of the electromagnetic spectrum. Although a blackbody is a hypothetical concept, a star's radiation output closely matches a blackbody radiation curve. If the surface temperature is known, the dominant wavelength can be determined using Viens Law. where the dominant wavelength is equal to Viens constant divided by the surface temperature of the star in Kelvin. Our Sun has a surface temperature of 5,778 Kelvin. If this is substituted into the equation, we can determine that the wavelength of maximum intensity emitted from the Sun is approximately 502 nanometers, which is within the visible part of the electromagnetic spectrum. As we examine the blackbody radiation curve of stars, two different effects are observed when we increase the temperature. A cool star, such as the red dwarf Wolf 359, has a surface temperature of approximately 2,800 Kelvin. The wavelength of maximum intensity falls within the infrared part of the electromagnetic spectrum, and the radiation being emitted is very small. The colour of Wolf 359 is red because the small part of the visible spectrum that is emitted is mostly at the red end. Epsilon Indi has a surface temperature of 4,600 Kelvin. The blackbody curve approximation reveals that the wavelength of maximum intensity decreases into the visible part of the spectrum and the radiation output increases. Epsilon Indi appears orange. The Sun, with a surface temperature of 5,778 Kelvin, has a wavelength of maximum intensity of 502 nanometers in the middle of the visible spectrum, and outputs far more radiation than Epsilon Indi. When viewed from space, the Sun appears white because all of the different wavelengths emitted over the visible part of the electromagnetic spectrum combine. However, when viewed from the surface of the Earth, it appears yellow due to the Earth's atmosphere, not due to the wavelength of maximum intensity. When star temperature increases further, the wavelength of maximum intensity goes beyond the visible spectrum, but the part of the visible spectrum that is being emitted is more towards the blue end, so very hot stars take on a bluish hue. Stars are classified based on their surface temperature and luminosity. When stars are examined on a HR diagram, it is no surprise that the brightest stars in the night sky are mostly luminous blue stars and red giants and supergiants. These stars are often at vast distances from the Earth but are so luminous they appear very bright. The brightest star in the sky, apart from our own Sun, is Sirius. It is only the brightest star because it is rather close, and although it is far more luminous than our own Sun, its luminosity is very small in comparison to most of the other brighter stars in our night sky. When we plot the nearest stars, a great truth about the universe is revealed. The most common type of stars are red dwarf stars, which constitute a significant proportion of the stars that are closest to our own Sun. They are far less luminous than even our own Sun. In fact, the closest star to the Sun, the red dwarf Proxima Centauri, cannot be seen with the naked eye and requires a mid-range telescope to see.